So yes, all right. So let us do a quick recap of what we did yesterday. So let me share my screen. Yeah, so yesterday we looked at fundamentally first the perceptron, and I want to give you all this sort of disclaimer that even though some of the math can be scary, particularly the calculus and the derivatives, it is not necessary to understand the fundamental concept that I am teaching. So if you're don't have as strong of a math background, feel free to gloss over some of those details and just focus on the higher level concepts. So let's quickly go over what you learned last week. So as we mentioned, yesterday, a perceptron is something that takes inputs, right? And it weights the importance of each input and then applies a non-linearity function, which we call G, to give you some output. As we showed, this nonlinear function could be, say, a sigmoid, which squashes the output between 0 and 1, a ReLU function which assigns an identity for values greater than 0, identity meaning it assigns the same y value as the input x value, and it assigns 0 to any value less than 0. And this is an example of a nonlinear function. And as we were explaining, we need nonlinear activation functions to sort of capture the nonlinear space of the data, the nonlinear space of the data. Because if we just only have linear functions, which is just fundamentally a straight line, we cannot sufficiently separate the data. So with this simple building block, we can build what we call complex deep neural networks. And all that essentially involves stacking layers of these perceptron units. So in this case, this is our input, and then we have multiple layers. This is an example of a particular layer, but we can have many layers like these with many different types of units. And then we have some final output layer. And essentially, when we initially start, when we initialize a neural network, it doesn't know anything. It's simply, for example, just going into an exam without ever having done any sort of studying. Some people might, I don't know, some people that is possible. For me, that is very difficult. And similarly for a neural network, if you have never what we call trained the neural network, it doesn't know anything. So once you apply it to a particular task or data set, it doesn't perform well. So how we get a neural network to do anything actually practical is that we need to train the neural network. And how we train a neural network is using what we call a loss function. And the loss function is some sort of signal that tells the neural network how good or how badly it is doing at its particular task. So in this case, for example, when we were looking at this example here, when given this input, the neural network predicted 0.1, but the actual ground truth, or what output it should be assigned, was supposed to be 1. This difference is called the loss. And given this signal, we need to update the weights of the neural network to factor in these mistakes that it made. And in terms of updating the weights of the neural network, this is a term we call back propagation, where essentially we just apply the chain rule, which is essentially applying multiple derivatives to update the weights of the neural network. And that, as you see here, we have the loss function and we're trying to get to the minimum loss. And essentially we have a starting point, and then we keep on taking the derivative, which is just some sort of signal based on the value of the loss and the current setting of the parameters of the neural network. It tells you which direction you need to go to on the loss landscape to move in the better direction. And eventually, by following the signal of the gradient, it's able to get to the minimum, hopefully, of the loss function. And at that point, it is the optimal weights of the neural network, and it has been properly trained. And as you see here, this is how we update in weights. We take the gradient. It's nothing too crazy. It's just the signal that the neural network uses to figure out which direction it needs to go. Then learning rate tells it how confident or how much big of a step or how much we should trust the gradient. And then we update the weights W of the neural network in the opposite direction, meaning we take the negative of the gradient because the gradient gives us a direction of steepest ascent while we want to go in the direction of steepest descent. So we take the negative of the gradient and update the weights accordingly. And so someone asked, how do you guard against convergence to a local minimum? So as you can see with this complex loss function, a local minimum is essentially, say, like a point like this, while this is the global minimum because it's the lowest point on the curve. And that is one of the tricky parts of training neural networks is it can get stuck in what we call local minima. But using a combination of different sort of training training tricks, like for example, correctly setting the learning rate using an adaptive optimizer, correctly setting the batch size using regularization, we can sort of hopefully escape the local minimum and actually able to reach the global minimum. Yes, so that is sort of a brief recap. And today we're going to look at sequences. So what are sequences? Sequences are basically everywhere. So you could think of a sequence as basically a time varying sort of signal. And the data could be audio, for example, which changes over time. Or for example, text. So this also is a sequence. Life is a sequence of different sorts of events. And what we're trying to do with neural networks is figure out a way on how we can properly model sequences. So one simple way to model a sequence is simply to just predict the next word. So for example, if I give you this context, I am enjoying this artificial intelligence as a context. If you were able to predict the next word, given this context, you would probably predict course. And this is what essentially we want our neural network to be able to do, is that if it can model sequences properly, if given some context, it's able to predict the next sequence or the next token. So one way that we could do this is essentially using a fixed window of words to predict the next word. So in this case, if we look at the two preceding words, in this case, artificial intelligence, it doesn't, to predict the next word, it is slightly ambiguous because it could be artificial intelligence robot, it could be artificial intelligence program. And you basically have this problem where you cannot really model the long-term dependencies needed in the context to predict the next word. So for example, here, if we only look at the last two words, in which in this case is speak fluent, we won't be able to capture the context of, say, Venezuela, which would give us the indication that that fluent would indicate Spanish, right? So we need information from the distance passed to accurately predict the correct word. So essentially looking at fixed preceding two words, which we call n-grams, is not enough to predict the next word. So we need to think of something different in order to model these sequences. So another idea is that we can essentially count up the number of words in the sequence, and based on these counts, we can predict the next word. This is what we call a bag of words encoding, meaning that we essentially represent a sequence as essentially of counts of each word. So for example, if morning was mentioned in the sentence twice, we would have a count of 2 for the word morning. And let's say if the word I was mentioned 3 times, the count would be 3. So if you look at this representation here, it essentially encodes the count of each word. But the problem with that is that it doesn't preserve order. So even these 2 sentences here, even though the counts of each word are exactly the same, the semantic meaning is obviously very different. So the most probably like straightforward thing would be to sort of use a really big fixed window to predict the next word. So in this case, we're using the entire preceding context to predict the next word. But the problem with that is that we don't really get to sort of, if we just encode the context, each of the words of the context separately, we don't get to sort of model the interactions between different words in that context. So for example here, enjoying an artificial intelligence plus the word I, the combination of these 3 words in the context would probably give the indication that this is a course rather than say like a robot, for example. So being able to model the interdependencies and the intricacies between words rather than modeling them independently, meaning that we model them in isolation rather than as in codependence, we cannot fully understand the context of predicting the next word. So essentially, to model sequences, we have to think of fundamentally 4 different things. We want to be able to handle variable length sequences. So sentences or sentences could be 3 words, it could be 10 words, and we should be able, our model should be able to handle the variable length of these sequences. Secondly, it should be able to track long-term dependencies, meaning that if, for example, we have a sentence that's say 20 words long, it should be able to factor in what was mentioned at the beginning to sort of understand a group, to have a global understanding or representation of what the sequence is describing. We obviously want to maintain some information about the order, because obviously the order of words in a sentence or the order of a sequence is very important. And we want to be able to share the parameters across a sequence to be able to encode the intricacies and the interdependencies between these different words in the sentence. And we have a different type of neural network, which we call a recurrent neural network, which is a popular way of modeling this sort of problem. So yesterday, we learned the standard, what we call feed-forward network or multi-layer perceptron. And what it does, it essentially models a one-to-one relationship, meaning that it takes some input, it passes it through several layers of multi-layer perceptrons, and then it outputs an output. However, for sequences, we want to be able to model stuff over time. So we need to design our neural network to model the temporal dependencies and address the criteria we just mentioned. So in the case of, say, for example, sentiment classification, which is what we're going to look at in the coding exercises today, we want to be able to assign some label to the type of, to whether the sentence is a positive or negative, and has a positive or negative connotation. Or a many-to-one relationship, we want to basically do music generation. So given some sequence of musical notes, we want to predict the rest of the musical piece. So these stuff are what we call many-to-one and many-to-many relationships. And in both these cases, there is some temporal aspect to it. And we want to be able to model the time in these sort of data. And therefore, recurrent neural networks are the de facto method. So in the standard vanilla neural network, which we looked at yesterday, as I said, we get some input X, we map it to some output Y. With a recurrent neural network, we sort of have what we call a hidden state, which we update each time step, and we use these same parameters for each step of the sequence. So what that looks like is that we have some hidden state, ht of -1. And what you can think of this hidden state is that it encodes the context up to time t. And then you have your current token x of t. So given your context and your current token, you want to be able to output or predict the current token or the current hidden state h of t. And it's in this, it's very simple. If you look at the diagram, x of t is the input, h of t is the context. And given your context and your current word, you want to output the current context. And we use the same function and set of parameters at every step. So we have some input vector xt. We have an updated hidden state, and this is just matrix multiplication. For those who don't understand the math, it's all we're doing is that we have some weight matrix that essentially encodes the hidden state and then also encodes the current token x of t. So we just essentially apply one neuron or one perceptron which takes an input. It applies a weight matrix and gives you some output, and we apply the nonlinear activation function tan of h, and that gives us our updated hidden state. And then for the output vector, we apply another weight matrix to get our output. So honestly, a lot of neural networks is simply just matrix multiplication. Usually we have some weight matrix, which we multiply by some input, and it gives us an output, pretty much. So how you could think of this is if we unroll this recurrent neural network over time, you essentially have you represent the first token x of 0, then you represent your next token x of 1, x of 2, and then till the end of the last token in the sequence. And then you have your weight matrices, which, as we said, it takes some input, it gives you some output. So you have a weight matrix for the input. You have a weight matrix for your hidden state, and then it gives you, it encodes both of these, and it again gives you the output. And key is that we reuse the same weight matrices at every time step, because as we said before, we want to share parameters so that we can model the interdependencies of different words at different time steps. So we want to share the parameters so that we have this interdependence and this inter-understanding. So as you can see, if you look at this neural network on a very much high level, one, you can see because we have, since we sort of roll it over time, it is modeling the temporal aspect of a sequence. Secondly, because we share the parameters, it's able to model the interdependencies of different tokens at different parts of the sequence. And because we do it in a sort of sequential manner, it also factors in the order of stuff in a sequence. So while, for example, in the neural network, the regular neural network or the vanilla neural network that we looked at yesterday, where it just takes some input and maps it to some output, it doesn't factor in time, it doesn't share parameters across a sequence. This recurrent neural network is specifically designed so that we look at data temporally. We share parameters of the model across the different parts of the sequence, and it factors in the order, which makes it well designed for sequences. And similarly, we need to train a neural network. So we need to have a loss. And what the loss does, it looks at the output of the recurrent neural network at each time step. It calculates the difference, sums it up across all time steps, and then averages it across all your samples in your data set. And there was some confusion about backpropagation. All backpropagation is the fact that after you calculate your loss, you need to update the parameters of your neural network to factor in the fact that it made some mistakes. So backpropagation is just a big term to describe that we update the weights of the neural network using the chain rule, which is essentially repeated applications of using the gradient to update the weights of the neural network. So if you recall, for backpropagation in a feed-forward network, we have these different layers of perceptrons. So X is the input layer, the green is the hidden layer, is a hidden layer neural network, and Y is the output layer. The hidden layer has 4 units, the input has 3 units, and the output has 2 units. And if you could think about on a conceptual level what a neural network is doing, it does what we call a forward pass, meaning that given some input, it maps it to some output. Then you measure the loss, which tells you how off is a neural network from what we wanted to predict. And then given this signal, it needs to basically update itself. So for example, if you do a problem in, say, homework, you write out the solution and you give it to your teacher. The teacher will sort of like basically in red tell you the different mistakes that you make. And then based on those mistakes, you now understand the mistakes that you make. So if you encounter a similar problem again, you know how to approach that problem. It's basically the same thing. So essentially, the neural network does a forward pass, meaning that it attempts a problem or it attempts to make a prediction. And then we use the loss, tell the neural network, oh, you were bad by this amount on these examples. And then essentially the red is sort of teacher corrections where it must update itself to sort of factor in the feedback that it gets from the loss. And this sort of updating the parameters to sort of factor in the feedback is what we call backpropagation. And that is, I need to get backpropagation for all of the weights, which is why, for example, forward, you see the red line, and then backward, which is sort of the corrections, is the red line. So it goes forward and then backward. And that's pretty much on a high level what a neural network is doing. In the case of an RNN neural network, because we have outputs at each time step, we also have to factor in the errors at each time step. So the forward pass is the black line. So essentially it goes to the loss. The loss tells the neural network, oh, you were bad in these instances by this amount. And then you have to update the parameters. And the parameters here are represented pretty much by the black lines. And essentially the red lines is the sort of gradient or the sort of backpropagation that updates these parameters to factor in the mistakes that the loss in its prediction, which is represented by the loss on a high level. That is the biggest takeaway. So basically, forward pass is when the neural network makes a prediction. The loss tells the neural network which mistakes it make and by how much. And then backpropagation is essentially how we update the weights after factoring the mistakes that the neural network makes, so that the next time it hopefully doesn't make as bad of a mistake again. So with the RNN, you essentially have what we call multiple applications of the weight matrix. And if you have a very long sequence, what ends up happening is that on the backward pass, if you have if your gradient is either too small or too big, multiple applications of small or large gradients would give you a very would sort of either explode or shrink. So if your gradient is greater than 1 and you keep on multiplying values greater than 1, you get an exponentially large or exploding gradient. What that means is that you're sort of losing, as you said, the gradient is how we sort of learn, or that's the training signal. So we want to clip the gradients for very big gradients. And if, for example, you have any small values, as you multiply many small values, you get much more small values. So this is what we call the vanishing gradient problems. And there are a few ways to tackle it. One is the choice of the activation function. 2 is how you initialize the weights. And then 3 is the network architecture. So as I was sort of alluding to, with the vanishing gradient problems, when you multiply a lot of small numbers together, you get the errors, which I get much, the errors much further in the sequence gets much smaller and smaller gradients. And the smaller the gradient, meaning that you cannot get enough useful training signal to update the weights. So you want to have you want your gradients to be of a decent size, so you sort of are able to learn. It's like, for example, if for example you do a problem and then you give it to your teacher and they don't give you any sort of red marks or corrections, you do not know how to sort of tackle the problem the next time. It's a similar case. For the neural network, the gradients is how it teaches, is how it is taught, and it needs to have decently sized gradients for it to learn. And since it cannot capture long-term dependencies, because it cannot have gradients over a long temporal scale, the parameters then instead capture short-term dependencies instead, which we do not want. Like, language is extremely complex and we want to be able to capture it over a long term. So as I said, one way to solve this problem is to use different activation functions. So traditionally, the tanh activation function was used, but ReLU prevents a lot of this shrinking on the gradients because the derivative is positive above 0. And then for parameter initialization, we sort of initialize weights to identity matrix, which is basically a matrix with all ones along diagonal. And then we initialize the biases to a 0 matrix. And then this helps the weights from shrinking to 0 during back propagation. And then the most actually beneficial thing is to use more complex recurrent units. Even so, so the two most popular ones are LSTMs and GRUs. LSTM stands for long-term short-term memory, and they use this sort of like gated cell mechanism to control information flow so that information can be propagated back many time steps. And a combination of activation functions, weight initialization, and these sort of gated recurrent units, we can get to model very long-term dependencies in sequences like language. And RNNs are extremely influential. It was the sort of standard way to model sequences up to maybe about 2 or 3 years ago. It can be used for music generation, where given some input of sheet music, you want to predict the next character. So similarly, given some context, you want to predict the next token. In this case, the context is some starting notes of music, and then the next token is the next token you want to predict, and you keep doing that until you sort of generate an entire piece. Then the next one is sentiment classification, whereas what we're going to look at in our exercises is given some sentence, you want to decide whether it's a positive or negative sentiment. In this case, I love you is a positive sentiment, while something else would be classified as a negative sentiment. And then probably one of the most powerful applications of RNN, this is what at least used the power of Google Translate, which some of you all maybe have used if you've traveled to countries where they don't speak English. So RNNs are used in what we call an encoder-decoder structure, where you first encode the source language, and then you sort of decode it to French and then compare. And it uses the same sort of fundamental concepts of recurrent neural units, such as RNNs. And this is what powered Google Translate powers for like the longest while. And then we sort of use an attention mechanism, which allows the network to focus on particular parts of the input when it outputs its translation. Because as you can imagine, certain parts of an input matters more for certain parts of an output. So being able to sort of attend or focus on different parts is extremely powerful. So in summary, deep learning for sequences is extremely powerful. Particularly, we use recurrent neural networks, particularly because it's well suited for sequence modeling tasks. One, because it factors in order. Two, it shares parameters across different parts of the input, allowing you to sort of capture the interdependencies of different parts of the sequence. And then three, it allows you to model extremely varying length sequences over time. We train in neural networks similarly with the vanilla standard neural network with backpropagation, but we need to backpropagate through time to factor in the fact that we have errors at each step of the sequence. And these can be used for a variety of applications, particularly music generation, classification, and machine translation tasks. So that is it for the lecture. If anyone has questions, please post in the chat and I will go over any particular part that is confusing. So question, does Google still use RNNs for translation? That is a no. So in 2017, there was a new neural network called what we call a transformer, which is better able to capture the dependencies of pairwise relationships in sequences. And this is now the de facto way to model sequences as of maybe a year or two ago. And we're gonna at least play with the popular transformer neural network in the coding exercises called BERT, which is extremely popular. So let me see if there are any other questions. So RNN basically used for time series problems. So yeah, I think so. It's like transformers are pretty new, so like it hasn't fully etched its way into every sequence problem. Though for like I think like time series applications, I think particularly for like modeling financial markets over time, RNNs are still sort of the de facto, but the sort of paradigm is shifting towards these transformer models. Some more of these transformer models. Yeah. So let me see. So there's questions on more in depth with the coding. So I can go over the briefly go over the one from yesterday. So as I said, we're using PyTorch, which is a framework built on Python, Python is a programming language. And we are using a Google Colab, which allows us to essentially quickly run Python applications and quickly have access to GPUs, to a GPU to train these models, which are extremely important. So if people need access to the Colab, I think it's posted on the pptbrightminds.com, which you all probably are used to it, and the coding exercises are here. Instructions are simple. You open the link, you log into Gmail, and you click File, Save a Copy in Drive, and then you essentially click edit notebook settings, and then you click hardware GPU. So we'll go over this coding exercise after the Q&A, as well as the one from the one for today. But I would not right now. I'd like to introduce our Q&A speaker for today, Nicholas Fuller, who Dr. Fuller to be more exact, and I'm excited to have him today, particularly because he's one of my mentors, and is a director at IBM Research, focused on cloud hybrid services, and has an extensive application of has an extensive history of developing cutting edge technology and innovation at both the theoretical and sort of practical level. Has been at IBM for I think 20 plus years now, and has a wealth of knowledge. So how it's going to be sort of play out is similar to yesterday. I'll probably ask a few questions at the beginning, but I would take it as an opportunity for you all to sort of ask questions about advice or anything that interests you all. So Nick, welcome.
Thank you, Mandela. Can you hear me okay?
Yep, I think we can hear you all well.
Fantastic. I wore my Fatima polo shirt especially for this event. So
only Fatima people in the house, y'all could blow up the chat, by the way. So yeah, welcome. I think just giving like a little background about your sort of like your journey from Trinidad all the way to sort of like your position now at IBM, what got you excited, sort of, and how was sort of like your sort of experience growing up in Trinidad probably was influential in sort of like your journey.
Awesome. Thanks again, Mandela. Given the timeline that we have, I'll make that intro fairly brief. Certainly want to entertain questions from folks who are part of this discussion today. So I attended Fatima, as I mentioned before. I see one of my former classmates here as well, Jeff Sion. We graduated in 1992. At a time when Fortran was the thing, right? And Jeff would be a person to share a whole lot more about that. After taking a break for a year, I did my bachelor's degree in Atlanta at Morehouse College in physics and math, spent some time in computer science as well there, working on some NSF activities, and did a number of internships. One of the things that to me is very critical at any stage of your career actually, or education, is trying to figure out what it is you don't know. You don't know what you don't know is typically said. And so how do you figure out that missing piece is by engaging in mentorship activities, you know, having mentors who can help you, shadowing people and doing internships. So I did internships every year at Morehouse College in Atlanta. And that ultimately landed me at Columbia University in New York, where I did my PhD in applied physics, working on semiconductor devices. At that time, which is the period of 97 to 2002, traditional IT was still the mainstay in compute, whether it be for small, medium, or large enterprises. And figuring out how to aggressively scale performance through device shrinking, so-called Dennard scaling and Moore's law, which I'm sure you've heard about, was very much the hot topic for everyone to focus on. And so I did my PhD in that area. I also had some internship experience at Lucent Technologies, also a mainstay back then. And subsequent to that, joined IBM, working on building advanced devices. Now, I've been at IBM coming up September 9th for 18 years. In those 18 years, I've held multiple positions. When I joined initially, it was to focus on building next generation devices for IBM systems. Again, while traditional IT was still dominant. And I had multiple roles in that capacity. And after about the 10-year mark or so, I developed what I like to call the technical itch. Many of you, you know, as you go through your own journeys, and we are all at various stages of our journey, you will develop interest in other things that you would like to do. And so again, by figuring out what I didn't know, by asking questions, by shadowing people, by having mentors, I gradually migrated so-called up the stack, if you will, building on prior experiences that I had. as traditional IT gradually gave way to what is commonplace today in terms of the era of cloud and AI. And so today, as Mandela said, I manage a team as director of what's called Hybrid Cloud Services. This team is responsible for building innovation at the intersection of IBM's software and services business. And so I have a couple of quick snapshots that I'll show, actually, if that's okay, Mandela.
Yeah, for sure.
So let me share my screen. It says you've disabled participant screen sharing. Very smartly so, I might add. And that's okay if I'm not able to do it. But I'll touch on a few things, right? So I'm sure you all follow the news and various tech magazines, etc. Back in May, TechCrunch, Forbes, ZDNet, Bloomberg all carried an announcement that we made regarding IBM launches killer app for CIOs. What that referred to, it's an AI app that allows chief information officers at traditional enterprises to manage their applications. I'm sure you've had experiences where one or more services or apps you have of your own, or if you run a business, have had periods of outage. Outages happen from time to time, even in the cloud world, right? And figuring out quickly what is the cause of that is absolutely critical to a CIO from a revenue point of view. This is an area where, as a company, we have extensive experience, and my team has been building capabilities in that space for a long time. So what we did within recent time was to build on those capabilities and launch what is known as Watson AIOps, which is an application that runs across clouds as well as on-premise customer environments to help you maintain application uptime. It involves multiple AI technologies, from grouping disparate sources of data in terms of logs, system logs, application logs, events that come from monitoring systems, server systems, PagerDuty that site reliability engineers have access to, and grouping those data sources to filter out the noise, understanding the topology of the application, right? The footprint of the application, if you will, to ultimately help with root cause analysis so you can quickly resolve those issues. Cloud outages typically last several hours. Last year when I was home, I spoke at an event, and that event was a few months after there was a major WhatsApp outage impacting significant parts of the globe. And that was actually caused by an unauthorized configuration change by a system administrator. Just to give you an example. So there are many things that happen as a consequence that cause outages. And clearly for a CIO running applications, managing business critical applications that drive your revenue, this is an area that, of course, you cannot afford to have these applications stay down. Ultimately, you would like if you can predict if a failure is coming. So that's capabilities we're also working on. So things like predictive modeling, things like explainability, quote unquote, broader AI capabilities are part of that. Deep learning foundations are applied there as well, so as to be able to produce this type of application. So let me stop there. That's my quick background that I wanted to give you some sense of. Open it up to you, Mandela and team, to entertain whatever Q&A you might like to get into.
Perfect. So I think let's there's already a question from the audience, so let's just start there. So from Jose Monroy, the question to you, Nick, is what did you do to jump from, say, like a science physics background to sort of like IBM AI cloud type of research?
Yeah, so very good question, Joseph. So from the time you enter into a PhD program, and even if you don't enter into a PhD program, if you're interested in always asking questions and understanding why, right, that first of all is the foundation for someone who wants to engage in R&D. Now, what I'd like to say though, IBM research is a bit unique, right? You have, if you go back to the period, I would say before 1999 or so, IBM Research was very much an organization focused on publishing papers, right? Much like you might do in the academy as a university professor. We changed that significantly going back 20 or so years, where we coupled the research division to our business units. So for example, the point I just made about Watson AIOps, this is a product launched by our cloud integration unit. And we partnered with that cloud integration unit in a joint squad model to build out those capabilities. My team is still focused on figuring out how that innovation can ultimately be something they present at KDD, NeurIPS, Triple AI, etc. But ultimately, there's the innovation that comes about as a result of that work that can impact a product or a service. So that's number one. But in terms of so I think if you have that foundation, a research environment, certainly the one, at IBM Research and Industrial Research Facility is one that could be of interest to you. But in terms of the technical progression now, right? Because like, as I mentioned, bachelor's in physics, master's, PhD in physics as well, with some minor background in computer science, it really comes about by asking questions. So physics is a broad domain. My PhD is in what is called the condensed matter physics, the physics of materials. I did that for my PhD, got to IBM, did that. But then in the job that I had as a research staff member, ultimately I was working on semiconductor devices. And even there, moving away from what I had done my PhD in. Fast forward a few years, still in semiconductor devices, IBM was dabbling in alternative energy, photovoltaics, and I migrated into that as well because there's adjacent knowledge transfer, if you will, based on your fundamental ability to ask questions and to understand things. Now, the AI jump is certainly a bigger jump, the cloud AI jump, right, for sure, as opposed to going from semiconductor devices for microelectronics into photovoltaics. That jump came about gradually. My colleagues, and there are a few other people like me at IBM, my colleagues who stayed in device physics, they still look at me as if I'm crazy, right? Because they wonder how that's possible. Because again, they're far apart. But again, given where the industry was going, the emergence of cloud, the emergence of data, many physicists actually get to computer science through data science because that's what physics is. And so I began asking myself questions, began engaging in side projects. So that's one of the good things about IBM, actually. You can do your day job. Of course, you have to do it well, and you can dabble in other things that you have interest in. And so that's what happened. I gradually started playing in data science. And as I started playing in data science, I understood that, wait a minute, traditional IT is becoming, quote unquote, less critical. You're having the emergence of born on the cloud companies like Uber, like Airbnb, like Netflix, et cetera, right? And of course, traditional enterprises like Bank of America, Citibank, et cetera, taking a slightly longer time to get to that cloud journey. And that, in fact, that's a very different journey for a traditional enterprise. So that's the short story. I really loved, the idea of newness and diving into something that I can wrap my head around. I know I'm not the kind of individual who will do the same thing, say 10 years from now, but I couldn't predict when I was in Fatima finishing A levels that I would be here today. You sort of have to open your mind to what's happening around you. Keep yourself surrounded with a good network, ask questions, and it's okay to not know. I think that's the most important thing. Be comfortable with discomfort, be comfortable with not having knowledge in a particular space.
Sweet. So going on from a similar sort of question, I think people are interested in sort of the academia versus say industry route, particularly if you sort of like, I think people struggle with like, if they're going to do a PhD, like whether doing a PhD sort of restricted to sort of an academic sort of path, say the professorship, or versus say like what opportunities in an industry, say in giving a physics background or just a general physics PhD background would give you.
Yeah, and I recall you had a similar question, right? You were thinking about that anyway. You were deliberating when you were trying to figure out whether to do the PhD or not. Listen, the options are open to you. Many physicists, and I would say many PhDs in STEM as a whole, science, technology, engineering, and math, certainly do go into industry, and the numbers are available out there versus those who go into the academy. It really comes down to what you want. Having had experiences before when I did my internships, both at Morehouse for my undergraduate degree and at Columbia for my PhD degree, that straddled both. I did academic type research when I was at those institutions, which was interesting. It's a more methodical, slightly longer time scale process. When I did internships in industry, like Lucent Technologies, for example, and I also interned at a Tyco Electronics subsidiary in Boston, 1996. Those experiences actually had a different impact for me. I really loved how I was able to do fundamental work that ultimately was impacting some product trajectory, right? And still able to potentially publish alongside with it. That for me was the holy grail. And so it naturally propelled me into looking to industry once I graduated. But I think the option is up to you, right? The multiple options are available. And it really comes down to individual choice and what you think you might want to do ultimately.
Got you. And how you talked a lot about sort of like mentors you've had in sort of like your life. How did you go about sort of like sourcing these mentors, and any advice would you give for people who are sort of like looking for mentors as they sort of go on this sort of journey through, say, into this sort of journey?
Yeah, very good question. So I had a mentor actually who was not a technologist at all when I was home. He was a high-level executive in Citibank, Trinidad. And, you know, your mentor doesn't have to necessarily come from your domain. Certainly having mentors in domains you're interested in help, okay, in terms of figuring out how to navigate your career and so on. But it's almost like a sounding board check, okay, as far as thoughts that you have and so on. So how do you source them? You know, network, right? We're very sociable people, right? Trinidadians, Tobagonians, Caribbean people at large. I think leverage that social aspect of your personality for sure. Be okay, be open to saying what it is you don't know, why it is you want to seek out having a relationship. I think that's fine, right? And in that type of approach, many of the mentors I've met have been through me seeking, and some of them have been, you know, almost without me seeking. So Mandela, you yourself, you pulled me into the Tech Beach conference. At Tech Beach, I met many people who were doing really progressive things from a technology point of view throughout the region, and multiple relationships have spawned since then. You have no idea how a given intro, a given meeting, a given participating event that you make some time for, how that ultimately can help you connect the dots. Many of my mentors actually came through unplanned activities from just being social, being aware, and connecting with folks. And that by far has been the more pivotal part for me in terms of career navigation.
Oh, that's really powerful. And going on along that sort of pathway, I think people seem to be interested in, like, we're in this sort of 21st century where everything is super competitive. Say there's, and how do you sort of like differentiate yourself? How do you sort of like differentiate yourself, especially when you think of like this being a global economy and globalization where you're competing with people from all over the world, and where information is so widely accessible on sort of the internet as well?
Yeah, it's a fantastic question. Listen, there is no greater time to be a computer scientist. No greater time. Just think of what's happening right now, okay, in terms of our mode of communication through Zoom, running on AWS infrastructure that none of us are thinking about as we dialogue, okay? You assume that to be a given, okay? Think of distance learning. If you have kids, I have kids, they were engaging in distance learning. Think of all the capabilities you take for granted that run on some cloud infrastructure, that have some additional set of services running on cloud, perhaps leveraging AI and so on. It's a fantastic time to be a computer scientist. And there's no, I would put it this way, right? Distinguish yourself by being passionate. So number one, the opportunity is there, okay? So don't worry about supply. Don't worry about being in a crowded space. There is so much to figure out in terms of AI. We're in that broader AI. If you think of AI having a taxonomy of narrow, broad to general, we're in that broader domain, learning from less data, transfer learning, low shot learning, explainability, and so on. Trust, bias detection, that's AI. Security, similar concerns, quantum computing. There's a huge growth that's happening in this space that also is marrying what happens from a software and hardware point of view. So there will not be an oversupply issue is my declaration. That's number one. But be passionate, right? That passion is going to bring you to, you know, or discover what your passion is. That's going to bring you to, hey, what it is I really want to do? Because that's number one. You have to be able to get up every day and do this thing. If you don't like it, I guarantee you're not going to last in it, even if there isn't a supply issue. Right? So while the financial piece, the supply piece are all important things for you to think about, passion should be driving you to what you go after. In my view, that's number one. You will find opportunity to distinguish yourself without doubt.
Wow, thank you. Thank you for that. And I think sort of similar sort of question. I think people are interested in sort of advise, particularly if you don't say come from a particularly say STEM background. So say, for example, if you have say humanities or say economics, how does one sort of get involved in sort of like this digital age? If you say have already decided to say do a non-STEM background, if your background is non-STEM.
Yeah, listen, there's an individual who runs something known as the Global Tutoring Hub in Barbados, and actually that's taking off, particularly in the era of COVID. So, essentially a distance learning model that they're exploring in Barbados, who I happened also to meet at Tech Beach in 2018. And he himself doesn't come from such a background, right? And has navigated in this space. I think there are multiple courses out there, Coursera, you name it. There's a ton of online courses to help you climb that learning curve. We actually, as a company, offer something known as the Skills Academy for both individuals and professors to make that transition. IBM also is partnered with a number of other companies in something known as PTech, Pathway to Technologies. There's no shortage, if you will, of resource that helps you to navigate and get into some level of comfort level that resonates with what you want in this growing technological economy and globe. Again, emphasized only by how COVID has put that strain on us as a global population. So in my view, leverage those resources, leverage Mandela, us as panelists, right? This doesn't have to stop here. I caught one of those questions higher up in the chat, right? I'm happy to be a part of, future mentorship if that helps for any individual who would like to connect. These are really important times, and being passionate about what you do, finding the right set of mentors. And if you come from that different background, that's okay. Multiple resources out there for you to take advantage of.
Sweet. And any sort of like any lasting words before you sort of, before you go?
It's great to be here. It's wonderful. I want to commend you and your team, right? Working with BP, right? For setting this up. And there's a question regarding contact info, right? Mandela, feel free to share that, right? You know what to share. You have all my contact info. Happy to be part of that follow-up. Be passionate. I want to make that point. And last but not least, much like Mandela and team have set this up, this is about growth, right? This is about each one teaching one. We're in an environment, I feel the need to mention this. We're an increasingly difficult environment globally, not only because of COVID, but also because of the rise of populism, right? That's impacting the view people have across the globe. And none of this would be possible if Mandela said, well, I'm going to only focus on my kind, okay? Or I said to him, help me understand if this is only focused on my kind. What is that? We're in a globe, people. And this globe and borders are shrinking. When you learn, give back, right? There will be multiple opportunities for you to do the same. It's really important that we help grow this global village that we have so that we can all progress and make humanity better, onwards and upwards.
Sweet. Thank you so much, Nick. Thank you so much for taking the time, and we appreciate you being here for sure.
Awesome. Good to be here. Take care, Nick. Folks. All the best.
All right. Bye. Sweet. Let's move on. Thanks everyone for the questions. As I said, we're gonna have these pretty much every day with some really incredible people, pretty much all Trinidadians who are doing really incredible stuff. So I read up their bios, come with very interesting questions because they're taking times of their busy schedule to be with you. So take advantage of that for sure. So yes, so let's quickly go over yesterday's notebook because obviously it's a lot at the beginning. I totally understand. But the important thing I want to tell you is that everything is in these notebooks, and Google is honestly your best friend. So literally go through these on your own time, say after the session today, go through these on your own time. If you have any sort of questions or concerns, just make a quick Google search. But it hopefully is pretty clear. But what I'm sort of recommending is sort of it's not gonna come on the first day. I'm not but everything there, it's in a pretty hopefully friendly format, pretty clear. And if you have any concerns, reach out or sort of make a quick Google search. Sweet. So as mentioned, we're using PyTorch. So the two most popular frameworks for deep learning is PyTorch, which was developed by Facebook, and TensorFlow, which was developed by Google. And they both pretty much allow you to build and train neural networks at scale. And I picked PyTorch for this course because I am more familiar with it, and also it has become the sort of standard in academia and industry, and I think it's also a lot more user-friendly to use for beginners. So similarly, so if you'll have, there's also to point out, so let me share my screen again. Also to point out, there is this notebook on the course website on basics of Python and NumPy that people should take the time to complete if they don't have a background in programming. It is a pretty detailed Colab notebook. All you need to do is, as I said, file, save a copy in Drive, and then once it's saved, then all you need to do is edit notebook settings and put on the GPU. And then if you want to see all of your Colab notebooks, you click this button, and here you can see all of your Colab notebooks that you sort of save to your Drive. Yep. That should be clear. If there are any questions about that setup, please please post in the chat, but that should hopefully be clear. And so I think what would be good is if you all go through this with me. So so everyone, can you please open the notebook? The link is on the BPTT website for day 1, Monday 17th of August. You click the link, log into Gmail, if file to your copy in Drive, edit notebook settings, hardware accelerator equal to GPU. I'll give a minute for people to sort of hopefully log on. If you have success, can you please post in the chat, or if you have any problems, post in the chat. So yes, again, go to bpttbrightminds.com, which should be familiar. You click the link, you log into Gmail, then once you do that, you click File, save a copy in Drive, and then once that happens, let's say for example this, it opens a new tab, and then you click edit notebook settings and then GPU. All right. Seems like most people are getting it. So let's start. So to run a cell, it's very simple. You just click the run button. So let's all run the first cell. it takes a little time to initialize, and once it's connected, it moves pretty quickly. Let's run the next cell. So what this cell is doing, it imports the libraries that are very important for this, which is NumPy and then PyTorch. Here we're printing the version of PyTorch, and then here we're creating a NumPy. We're creating a NumPy array of a NumPy matrix of zeros of 2 rows and 3 columns. For people who are familiar with matrices, this would probably be very straightforward or intuitive. People who don't, a matrix is essentially just basically like a crossword puzzle grid, sort of like, where you have rows and you have columns. This specifies number of rows, and this specifies the number of columns. And PyTorch, you can do the same thing. You just do torch that zeros, and it creates a PyTorch tensor, while this creates a NumPy array. Fundamentally, it's the same underlying structure. It's just that with PyTorch, you can then put a PyTorch tensor onto GPU, which allows you to do much faster matrix multiplications, which is imperative for deep learning. These are all pretty straightforward. I won't go into all of these details. Someone says mine auto runs. So when you probably open a notebook, it already had the output from when I ran it. So all you just need to do is just run it again. It's completely fine. Yeah, so for example, it probably came with the output already. You just need to run it again. It's not big of a deal. So yeah, the main important thing is that you want to be able to move your tensors to GPU. So you use the .to function, which adds it to CUDA, which is a synonym for basically GPU. And we add it to GPU 0, which is what the colon 0 means. We could also move it back to the CPU. So yeah, we run this cell. So yeah, it takes a little while to move it to GPU initially. And then we move it to CPU, back to CPU, just to show that you could go back and forth between CPU. So as we went in so people are asking CUDA 0 or can we use CUDA 0? What does CUDA 0 mean? So you can have multiple GPUs, and if you here we're specifying that we want it to be on the first GPU, meaning GPU 0. As I've mentioned, everything is 0 indexed. Everything is 0 indexed, but I think Colab only has 1 GPU, so we're just using the first and only GPU. But if you have multiple GPUs on what we call a node, you can specify other GPUs, or if you wanted to run on multiple GPUs, you could just remove the colon 0. Here's a bunch of imports, which we can run again. Need to run, and here we just set the device to CUDA if CUDA is available, which it is. Else, if CUDA is not available, we put everything on CPU. And as I mentioned, and you'll see in the other notebooks, I've tried to make it so that it's all the similar sort of recipe. And yeah, so yes, everyone, if people are posting questions, if you can help each other out, that would also be great. That, as sort of Nick said, we need to sort of help each other out. So if people sort of understand, please feel free to answer in the chat if they can be of help. So yeah, basically the 5 main steps are: you need a data set, you need a model, you need a loss function, you need an optimizer, and you need and then you have to actually train the network. So these just set everything up, and then the last step basically puts everything together and runs everything. So here is basically code to download the data set. So here we download the data set, which what wget does. So wget downloads something from a link. Then we sort of, and then we unzip it using this command. It's not too important in the grand scheme of things. And then what we do is we define a PyTorch data set. And what a data set does, it allows you to specify how you want to basically package your data. So essentially the main functions you need to define is the init function, which does any sort of special preprocessing that you need. Here we do a very vanilla preprocessing where we just, for example, get all of the images. And if we preload them, we save them in as a data structure, as a set of lists and a set of labels. And then the main function that is important in a dataset class is the get item, which takes an index. And the index basically, you could think of your data set as a list of, say, images, and an index indexes into a particular image. And here you need to open your image and then also specify the label. The specifics of the code, I won't go into much detail, but at a fundamental level, you want your get item to return the important stuff that your model would need, which in this case would be the image for it to take in, as well as the label, which is the output that the model needs to predict. Here's how we open the image. And some of these details I cannot unfortunately go in over. You just have to sort of look it up afterwards. Some of these sort of more specific function, but on a high level, the get item is how you define how the image, and you define how you want your data to be sort of packaged. And in this case, you want it to return an image and its corresponding label, which is what we need to train a network. And then we also need what we call a data loader, which essentially defines how we batch a bunch of images together. So this just returns, the get item of a data set just returns one image. But usually, as we said, we want a mini batch of images. So with the data loader, we can batch a bunch of images by specifying the batch size. And because we want the data to be shuffled, because if your data is not shuffled, then essentially all of the images most of the images in a mini batch would be the same class, and then neural network could do what we call it is cheat. So when you shuffle the data, it gets a varied mix of images in the batch, and it cannot cheat as easily. Cheating meaning that it could sort of look for shortcuts, because if it sees that all of the images in a batch has the same label, it can sort of figure that out and it's not learn the structure of the data. Here we visualize the data set. And this is the important part to create a neural network. So that a question is about so someone asked about in this case is an image. So yeah, so a computer interprets an image as a set of pixels. A pixel is between 0 and is an integer between 0 and 255. And yep, and essentially we flatten the image into 784 pixels because it's 28 by 28. We define a hidden layer of neurons, and then we define an output layer of 10. So here, the layer takes the input. This is the number of units in the input, the hidden layer size, output. This is our activation function. And yes, the output defines the number of units per digit. So we want a probability per digit. So basically if we have, and in this case, it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. It's 10 digits. So we need to have 10 outputs, and the layer would give us a a probability for each output, which corresponds to the probability of this digit being assigned to this label. Yeah, so we could just keep running these cells. Here we move it to GPU. As I said, we define a loss function. So what a cross entropy loss does, it compares two distributions. In this case, the distribution for, let's see if I could pull it up quickly. It compares two distributions, particularly for the cross entropy loss. Essentially, it compares ground truth 1 to the probability assigned to that value, and it compares distributions, essentially. So that's what cross entropy does. So it gives the model, it tells the model how off you are based on your prediction. Then we need to have, as we said, an optimizer to optimize the weights of the neural network. Here we're using the optimizer called SGD, which is stochastic gradient descent. The details aren't too important, but the main thing that you need to specify a learning rate, which says how much to step, essentially. When we are looking at, it tells us how much, the learning rate tells us how much we want to weight the gradient. So basically how confident or not confident you want to step. Because as we've showed, if your learning rate is too low, it converges slowly. If it's too high, it oscillates. And then if it's just right, it sort of gradually goes towards the minimum, which is what we want. The momentum is a hyperparameter which also controls the how the gradient, how quickly to step with the direction of the gradient. It's used at 0.9. It's not too important as well. People ask, so the choice of learning rate is very dependent on the data. So you just have to try a bunch and then see which gives you the best performance. It's what we call a hyperparameter, meaning it's a parameter that we have to set that affects the model performance. And then this is a pretty standard what we call training loop. So what we do, we put the model in train mode. Then we go through epochs of data. An epoch is a loop through the entire data set. And then, so we want to loop through the data 5 times. And then here we loop through the data. So here, the get item returns, as I said, the data as well as the target. The output of the data is batch size 64. So if I print the shape of data, if I print the shape of the data and I print the shape of the target, I need to. All right. So yeah, if we trade it for 5 epochs, as you can see, the data. Yep. So you see batch size. So we have 64 images, and it's 28 by 28. And when we flatten this, we get 64 by 784, I believe. And then we have a label for each of the images. So we have 64 images in the batch. We have its corresponding labels and we want to predict the label given the image. And that's basically what's happening here in the trading loop, is that we get the data, we get the labels, we pass the data through the model, it gives us the output. Then we want to find the difference. We want to calculate the loss. So basically, what is the difference between what the model predicted and what the actual correct label is? Then we calculate the gradients. And then we update the weights given the gradient and the learning rate as we look at here. We update the weight given the gradient and the learning rate. We print some values, and yeah, that's pretty much it. And then here we show that the model actually does pretty well. It gets, I think, accuracy about 80 something percent, 88% or something was what I saw. So yeah, that's pretty much it. If you all have any questions, feel free to reach out, but I have to move on to the next collab today. So RNN, which is what we look at today. So I think this book does a pretty good job of going through sort of the high level ideas. So as we said, an RNN takes an input, a sequence of inputs, it encodes it and assigns some high level label. In this case, we want to assign a label 0 if it is a negative sentence, or the label 1 if it's a positive sentence. So here we do this. If we look at the steps, it's pretty much quite a bit the same thing. You create a data set, you create a model, you define the loss function, the optimizer, and then you train the model. And in this case, we're using a convenience library, which we call TorchText. So here we import TorchText, which is a PyTorch library as well, which is basically does a lot of text processing, pre-processing for you. And it has datasets built in already for you. So here we're using the IMDb dataset, which is a popular movie review website. And all you need to do is specify, so when you'll go through this more closely, you'll get go through it, but I'm just gonna, on a high level, go through the document, the collab. So here we load the IMDb data set, and it already gives us train and test data. Train data is the data we train on, test data as the test data that we test on. So basically we train, so basically you could think of training data as your homework, testing data as your final exam. You practice on your homework and you measure how well you do on your final exam. So it's a similar thing. So you train your model on training data, you evaluate it on testing data. So y'all could go through it with me, but it's pretty much just running a bunch of cells. But you would have to go through that obviously a lot more closely after this session. But I want you all to get the high level overview of what is happening. As you would clearly see, this is it's pretty much on a high level the same sort of concepts. You get it, you create a data set, you create a neural network. Your neural network is a function of the type of data. So for example, for certain types of data, you use a certain type of neural network. Then you define your loss, you define your optimizer, and then you train the model on a high level. So we're gonna see, so after you all go through this notebook, and this notebook, you would see that it's on a high level, pretty similar. The details, you'd obviously, people who have less programming experience would have to spend a little more time going through a lot of the details. But you just have to spend the time. But for the most part, it all works out of the box. You just need to run the cell. And it just is downloading the IMDb data set, which is a little big. So it's just taking a little while. So just waiting for this to download. It's probably taking a while for you all as well. Yeah, it's 50,000 movie reviews. So yeah, it's a non-trivial amount of data. So yeah, data is a lot of the most important parts of AI, getting the right data, processing the data in the right format. We aren't going to go into all the details of how to process the data because it's all very domain specific. But generally, the data and how you pre-process it is very important to get the right performance in your AI applications. So it's finally downloaded. So we have 25,000 training images, 25,000 testing images. And this is a random example from the testing data. So for example, so what it does, it already tokenizes the data, meaning that it takes a sentence and basically it splits it up into words or tokens. For people who are asking for the notebook, it is on the PPTT website. You just go to Tuesday and it's the first link. So people ask about the proportion of testing data and training data. So usually you want to have a lot more training data and a much smaller amount of testing data. So I think in sort of deep learning, 90 to 10 is a good ratio. 90 to 10 is a pretty good ratio because these networks are pretty data hungry, and you want to give it as much training data as possible, and only use a small proportion of testing data to make sure that the model doesn't overfit to your training data. For people who are getting errors, just make sure you run all of your cells. That's usually the problem. The notebook should work out of the box. And what people also do is they specify a validation set, which is basically a proportion of the training set that you use to measure the model performance during training. And the testing set is what you just is like. So basically, it's kind of like if you have a final exam, you shouldn't be able to see the final exam before you take it. It's a similar thing. So like in machine learning, training data is, say, for example, say your homework. Validation data could be, for example, say textbook problems. So it's problems that the teacher didn't give you, but it allows you to test still how well you generalize the problem that you didn't practice on. And then testing data is basically your final exam that you don't have access to, and all you have before was your homework and your textbook questions. People are asking, so I don't quite understand what someone means by utilize the full data set on the final model. I think your training data is used for training, and then and you're testing. So you partition your data into basically three things: training data, which is for training your model; some small proportion of your training data you use for validation, which is basically like your textbook problems to basically make sure that like your homework is not the only thing you're practicing on, and you sort of test how well you understand the homework on some textbook examples. And then your test data is you shouldn't look at until you finally trained your model and you've optimized it. That's your final exam, and that is one goal. Like your performance on your final exam, that's going to determine your grade for the class. So, and that tests how well you've understood the material. That's basically the sort of setup in a typical machine learning pipeline. So in unlike in images where we represent the image as, say, pixels, and each pixel is a value between 0 and 255. In sequences, in the sequences, we have to do a one-hot encoding. So essentially, we get a vector that is as long as the vocabulary in our data set, and we assign a 1 corresponding to the index corresponding to that word. So for example, let's say our vocabulary only had 4 words. We define a vector of length 4, and then if the word I corresponds to index 0, we put a 1 here. For Kate, we put a 1 in index 1, and vice versa. The beautiful thing about TorchText is that it does all of this stuff for you already, in terms of tokenization, in terms of one-hot encoding, and that's what these 2 lines do. And as you can see, We have 2,500 words in our vocabulary. Here we can print the most frequent words. And yeah, these are all just stuff to get a better sense of the data set. But a large part of loading in the data set and pre-processing the data set is done for you with torch text. So while here we had to define our own dataset class with a PyTorch dataset class, and you have to go through and essentially define the dataset yourself. Here, TorchText does this pretty much all for you, and you just need to go through the code a little more closely to see how they do it. And again, we define our batch size, which specifies how much sequences we look at in a batch. And we have to define a data loader, which in this case, they have a special data loader, which basically iterates over the data set. So the next thing is the model. So here we're using an RNN. So how the RNN works is that we have the one-hot encoding. Then we map it to what we call a dense vector. So all a dense vector is just just a vector of floating values. And then the RNN essentially takes it as input and then outputs the next hidden, it takes the past hidden state, the current representation of the input, and then outputs the current representation of the sentence. So what that means is that as we were going through in here, is that we need to represent the context and then we need to represent the current word. So the h of t minus 1 represents the context of everything before the current word. And we have the input course as the current word, and then you have to represent this as h of t. So if you look at the RNN, you have h of t minus 1, which is the representation of your context, up to t minus 1 tokens. You have your input, and then given your context and your input, you represent the context up to time t. Right, so this is our RNN model. So it's an embedding layer which takes an input and maps it to a dense vector. Then we have our recurrent neural network, and then we have a linear layer which basically tells us whether the sentence is positive or negative. The network is very simple. We take a text, we embed it. So we take the one-hot encoding, which we have talked about here. We embed it using the RNN. So but the RNN, we embed a one-hot encoding text into dense vectors. Then we use the RNN to essentially create a representation of the entire sequence. And then afterwards, we use the fully connected layer to output like whether this is a positive or negative, right? On a high level. So here we build our model. So the RNN takes an input dimension, which is a vector of the cited vocabulary. We want our embedded dimension to be 1, hidden dimension to be 256, and our output dimension to be 1, which is basically a probability. So if it's greater than 0.5, it is positive. If it's less than 0.5, it is a negative sentence. Our model has about 2.5 billion parameters. And here is the same loss function. We use a cross entropy loss. This time we use the same SGD optimizer, same thing. We pass in the model parameters and the learning rate. We move both the model and the criterion to GPU. Where is device? Oh crap. So yeah, device, I think I would need to. Yep, if there is, so you all may need to add this device actually to this cell. I think I forgot it. So just add this device to this cell because I didn't define a device. And simply the train function is this, like on a high level, it's all the same. You have your batch of examples, you pass it through the model, it gives you some prediction, you compare the prediction to the ground truth, which is the label, you get the gradients, you optimize the weights, and yeah, that's pretty much it's the same story. And then here we run it for 5 epochs again. So this is the number of times we go through the data. We train the model, it gives us our loss and the accuracy. We also evaluate the model on the validation data. We get a loss, we get the accuracy. And import time is not defined. I need to run this down. Yeah, when you're running these notebooks, make sure to run every cell because later on you get problems. Oh yeah, sorry, device device was actually defined here. I just never ran the cell. So you could ignore my message. But yes, like main advice, run all the cells. Make sure each cell is run. You know it's run if you see a number. You see a number. Yep, and then yep, this should run, and it's the same story. You want your loss to decrease, and you want your validation accuracy to increase. Is there a disadvantage to running too many epochs? So yeah, so as we explored in the first lecture, so yeah, I'm enjoying the questions. So if as again, if anything is confusing, please feel free to message in the chat. Yeah, so this graph is basically training loss. So you want your loss to decrease, right? You want to get to the bottom. You want to get to the bottom of the curve. So you want your loss to decrease. But eventually, for example, if you see the same homework example, it's like if you do the same problems, if you do the same sort of past papers all the time, you sort of what we call overfit to the past. Like if you did the same past paper like 5 or 10 times, you sort of what we call like overfitting to your training data. And at that point, you sort of learn the statistics of the training data too closely, and when it doesn't generalize well the data you have not seen. So if you train for too many epochs, you have this problem of the loss keeps on decreasing too much, but it only is learning the statistics of a training data, it overfits and doesn't generalize well. So what you need to do is what we call early stopping. So this is why the validation set is important, that you want to also measure your validation loss or your validation accuracy. And once it starts to increase, that means you're overfitting because you still are you're sort of overfitting to the training data, but you're no longer generalizing well. So you want to stop before that happens. If that makes sense. So yeah, so if we look at this training here, as you can see, so this is not the best model, I would admit. So the last notebook that we're going to briefly look at is a better model. And there's ways to improve this, but this is not meant to be a state-of-the-art model. It's just to get you exposed to the concepts. So a 50% accuracy, honestly, is not great for this task, particularly because if you just randomly guessed, your probability of picking the right answer is also 50%. So I'm not saying this is the best model in history, but it gives you the general structure of RNNs, how to train these models. You can optimize this stuff further. And I will leave that to those who are more curious to sort of look into that. but on a general sense, this is how you sort of train this model. And yeah, we train it for 5 epochs just to get a sense of whether the loss is decreasing, accuracy is increasing. In this case, it seems like it's not really doing too much. But yes, and then we can get a final accuracy. After this is finished training, it's on the last epoch. Sweet. And then we take that money value in the test set finally, and then it gives us yeah, 47.9%, 48%, which as I said is not amazing. So a better model, so y'all could go to BPTT Brightminds and go to link 2. So we didn't cover this in the lecture slides, but I felt the need to sort of at least expose people who are a little more interested in getting a sense of what is the current state of the art. So this is also on the sentiment classification task, and it uses a transformer model which we call BERT, and it is one of the state-of-the-art models that are currently being used for sequence processing. And I wouldn't, it's a similar story. I'm not going to run through the entire notebook. You all could take your time and run through it yourselves. But it uses this library, which we call Hugging Face transformers, which basically is a great library for people who are interested in sequence modeling or natural language processing in particular. It has all of the latest state-of-the-art models. It's super easy to play with. It only requires a few lines of code. And this notebook shows you quickly how to use it on this sentence classification task. So similarly, it's the same sort of stuff. You prepare the data set. As I said, tokenization is a big part of how you process text data. You need to map it to discrete tokens. You have to pad it because essentially these models expect a fixed size input. So you essentially find the maximum length of any sequence in the data set, and any sequence that is shorter than that length, you pad with 0, meaning that it's just not looked at by the model. And on a high level, this is the state-of-the-art model for sentence classification, for sentiment classification. It gets about what 82.4% in this class, which is pretty good. And the full BERT size model gets about 95% accuracy. So this notebook, it's for mostly people who are more interested in getting to play with some of the latest state-of-the-art models, particularly for this task, or just generally for sequence modeling. But I wouldn't say it's particularly important for people who are just getting started and want to get more familiar with for RNNs. So I'm going to just take questions for now. Please post in the chat. But that's pretty much it for the coding exercises. It all should run pretty smoothly. The text, these are comments. Please read the comments when you're going through this stuff tonight. It explains it hopefully pretty well. Yep. Could you do a test with the sentence to see how the model classify it? I believe I can. Let's see. So honestly, this is not great because the model isn't great at this task being at the current setting of this model isn't great at this task being 50 honest. Like it's less than random 50%. So it's not as exciting. It's not I would say that interesting, particularly for this because it's pretty much worse than random at the moment. But if you were interested in testing it on a center on a particular task, you would just do a forward pass of the model. So you have to just get an example, pass it in to the model. So this would be like a some sentence. This is a great day, but you'd have to tokenize this in the form that the model expects using the using the using the this spacey tokenizer that they're using. And then once it's in that format, you could just pass it in here and it gives you a prediction, and then you have to take the max for each time step. Just take whether it's take the probability, and then if it's greater than 0.5, it is positive. Less than 0.5, it is negative. Any more questions? So yeah, notebook should be, I would say, so it eventually becomes binary code, but we operate at the higher level of abstraction, which is Python and PyTorch. So can RNN be used for binary classification as well? Yes. So this is what it is being used for right now. So here we're classifying an image as a sentence either positive or negative. So this is a binary classification task. But as I said, it's a very flexible architecture. So we could do so this is a classification task. You have a sequence, which is represented by many tokens, and then you have some output. But then it can be used for many-to-many generation. So you have music generation. It could also be used for, as I said, machine translation, which is a many-to-many task. But sentiment classification is binary classification because it just gives you one output for the entire sequence. Anything else? Also, yeah, any feedback as well, please post in the chat as well, so that for lectures tomorrow and Thursday, we can factor it in. So from Gabriella, that is a good mental model of a RNN. So so yeah, so people were asking about the difference between a standard neural network and a recurrent neural network. So yeah, so this probably is a good mental picture. With a vanilla neural network, you pretty much just look at input to output. It doesn't really model time and the parameters, and basically what an RNN does, it is essentially a vanilla neural network where the parameters are shared over time. So, and it is explicitly used to model sequences. So you basically share the parameters for each different time sequence. So if you look at, if you unroll a RNN, essentially you have the same weight matrix that looks at the input. So XH means it takes the input X and outputs it into dimension H, and it also has the same weight matrix H, which takes in the input dimension, the input hidden layer, the input hidden state H, and outputs it to dimension H as well. So yes, and these are the same weight matrices that are used for each time step. And the point of that is because you want the representation of a token to factor in the past as well as the representations for previous input. So you want this interdependency. That's why you share the weights. But great question. So that's the fundamental point, is that once you understand fundamentally what a neural network is, a lot of these concepts are pretty much transferable. And it's all about how do you design neural networks to capture the structure in the data that you care about. So particularly, as you will see tomorrow, when we look at convolutional neural networks, which is trying to model particularly images or video data, because images are spatial data, you want to be able to, you want to encode this property of what we call spatial translation invariance. So for example, if you detect a concept in this part of the image, in the bottom part of the image, you should represent both the same concept in different parts of the image similarly, because it encodes the same concept. And you encode that prior in how you design your network to learn that sort of structure that you want. So basically, a lot of the field is how do you sort of, and so people who are interested in sort of transformers, I could quickly show you. Why is it so good is that it's able to capture this, dependency pretty well, where it looks at like each representation of each input is a representation of each other, is a pairwise representation of each other input in the sentence. So in this case, it's able to better encode the pairwise relationships of tokens in an input, which allows it to do pretty well. In terms of recording of lectures, it should be posted on the website. I'm not sure what the correct timeline is, but we try to get it up as soon as possible. Any more questions? Okay, let's call it a day for today. As I mentioned, please please look up the bios of the speaker tomorrow. She is one of the top researchers at Microsoft, researching in Cambridge in the UK, and is excited to speak to you all tomorrow. She does a lot of work on sort of medicine and mental health with respect to AI. People who have a more bio background, this would be a pretty exciting session, but please come prepared with questions. Thank you. And yes, any feedback, please feel free to message the team and we will factor it in.